So this is the part of the chapter where math is just going to explode all over. We are going to bring back stoichiometry, and we are also going to go over different ways of calculating enthalpy of reaction using various equations. But first, let's go and work through a stoichiometry problem. So here you have a reaction. It says that how much heat is going to be released when you combust 5.81 grams of acetone. So here is a few things. Here are a few things. I can English. You have to figure out what acetone is. It is right here. You're also given the molar mass of your acetone. So you have a way of finding that out. You're also given grams of acetone. Whoa, that is a highlighter. That is not a pen. You have your grams of acetone, and you also have your delta H of reaction for that whole process. So here is how you set this up. The first thing you have to do is start with the number they give you. You always, no exceptions, start with the number they give you. So that is going to be 5.81 grams. What is going to be your first step? Every single time you have to do stoichiometry. Convert to what? Convert to moles. You always convert to moles first. So you go to the periodic table, or you read the problem, and it tells you that in 1 mole of C3H6O, you have 58.1 grams over mole. 58.1 grams. Then you look at the balanced chemical equation. So in the balanced chemical equation, it tells you have 1 mole of C3H6O. The delta H of reaction can also be used as a conversion factor. So I release that many kilojoules of energy when I have 1 mole of acetone. I release that many kilojoules of energy when I have 4 moles of oxygen. So in this case, I have negative 1790 kilojoules. I multiply by all the top things, then I divide by all the bottom things. Through the magic of math, I get that my kilojoules are going to equal 179 negative. And you're like, cool, but all of my answers are positive. What are you doing here? Like, why are my answers different? So it gets into a little bit of vocabulary. So when we talk about heat being released, we are making the assumption that that value is already going to be negative. So in this case, my answer is going to be 179 kilojoules per mole. That is how we approach this kind of thermodynamics, thermochemistry problems as we add the stoichiometry. So here is going to be something that is going to come in super handy when we look at different calculations. So my stoichiometric coefficients are always going to give me an idea of the number of moles that I have of a substance. So here I have 1 mole of solid water being melted, and it requires 6.01 kilojoules for every mole of water that I melt. If I flip my equation, what that means is if I go, okay, instead of melting my water, I am going to freeze it. That is the opposite process. Because I am flipping my equation, I must also flip the sign of my delta H. Whatever I do to my equation, I will do to the value of my delta H. If I multiply by 2, I need to multiply that value of delta H by 2. Whatever I do to the equation, I must do to my delta H. Keep in mind that this idea does not carry over for second semester. We do other weird things there, but that is a future you problem. Today you does not worry about that. So also super important, we have to be mindful of our physical states. When we get into Hess's law, we have to be very, very, very mindful of the physical states. We cannot cancel things that are different. That is how things work. So we are going to look at why do we use delta H in chemistry instead of using internal energy. So one of the things that delta H is very useful for is just helping us understand processes that happen at constant pressure. And for all intents and purposes, those calculations hold up until 95% of the time. Where we start having issues in our approximation is when we start generating large numbers of moles of gas. When we start generating large amounts of gas, my delta H and my delta U start to differ. So I start to see discrepancies between those two values, and that throws off my calculation. When we have situations like that, what we tend to do is look at bomb calorimetry and see what is happening in those effects. However, this is General Chemistry 1. We are going to live and die by that 95% of the time that things work out. So we're going to say that 95% of the time, things work perfectly 100% of the time. That is how we live through chemistry. So let's go ahead and do a quick calculation and get through this. It says, calculate the change in internal energy when 2 moles of carbon monoxide are converted to 2 moles of carbon dioxide at 1 atmosphere and 25 degrees Celsius. If you remember in chapter 5, our standard temperature and pressure conditions were 1 atmosphere and 0 Celsius. In this chapter, standard conditions are 1 atmosphere and 25 degrees Celsius. Okay, so I have delta H. Cool. What I need to do now is find my delta U. I have to figure out what is it that I need to do. So I go back and I rack my brain to try to figure out how I can convert between delta H and delta U. So my delta U is going to equal my delta H minus my delta PV. After we simplify, we have that delta H minus RT delta N. We are making the assumption that we're going to be at isothermal conditions and our temperature does not change. So we go ahead. We have to figure out our delta N. So step 1, find delta N of gas. I look at my product. My product, Evy, has 2 moles of gas. In my reactants, Evy has 2 plus 1 moles of gas, so that is 3. So my moles of gas is going to be -1. Huzzah! Step 2, convert temperature. Why? Because for some reason we insist on giving everything to you in Celsius, when Celsius is completely useless and you need to always convert to Kelvin. So that temperature, you have 25 degrees Celsius plus 273 is going to equal 298 Kelvin. Yay, you! Okay. Now you have to say, okay, crap. There are about 75 different R's because chemists do not know what other constant to use other than R. Which R is this? Okay, here is how my brain works. If I am working with energetic terms, I have to use 8.314. If I'm working with gases, because I am not an engineer, I use 0.0821. What I mean by that is that in other classes like physics and engineering, your R is going to be given to you in kilopascals. So it's going to be 8.314. That is why we have about 7 different R's. They're all helping you find the same thing. So step 3, figure out which R to use. In this case, R is going to be 8.314 joules over mole times Kelvin. But notice, my loves, that my delta H is given to me in kilojoules. So if I use my R in joules, I have a unit mismatch. So I need to convert that R to kilojoules. 8.314 times 10 to the minus 3 joules over mole times Kelvin. Step 4, world domination, or, put everything into the equation. My delta H is negative 566 kilojoules per mole minus R, and I'm going to try my hardest to not mess this up, so I'm going to use parentheses. Parentheses will save your life. Use them. So you have 8.314 times 10 to the minus 3 joules over mole, kilojoules over mole. I multiply that by my temperature, so 298 Kelvin, times delta N, and delta N is gonna be minus 1 mole. So I go ahead, I multiply all the things. I have 8.314 times 10 to the minus 3 times 298 times negative 1. Evy gets minus 2.48 kilojoules over mole. Then I have negative 566 kilojoules over mole. I use my skills. Negative 566 minus negative, this is a negative here, 2.48. I get negative 563.5 kilojoules per mole. Okay. So this is your problem out here. Okay. So the next part of the chapter is going to deal with calorimetry. And calorimetry is how we measure heat being changed. You may see this in the lab this week. You may have seen it already. So my specific heat is going to be something that's going to help me figure out how much heat I can absorb or how much heat I am going to generate. So the specific heat of a substance is going to be how much heat I have to add in order to raise the temperature of 1 gram of a substance by 1 degree Celsius. I also have something called a heat capacity, and that is going to be an intensive property that depends on the mass I have. My Q is going to be found by doing MC delta T. So let's go ahead and try this out. The only way of doing this is by doing this. So this is how I write my Q's, by the way. I do the little stick throughout. So Q equals MC delta T. M is mass. C is specific heat. And delta T is going to be final temperature minus initial temperature. That is how you approach this problem. So I need to figure out the specific heat of water. So I go ahead, I go to the table, and it tells me that the specific heat of water, which is going to be a constant, is going to be 4.184 joules over grams degrees C. That is going to be the specific heat of water. So now I read the question. Do I have mass? Yes, I do. It's right here. Do I have an initial temperature? Yes, I do. Do I have a final temperature? Yes. Do I have the desire to work on this problem? It doesn't matter if you have the desire. You're going to do it anyways because we have to. So my Q is going to equal my mass, 466 grams, multiplied by the specific heat, 4.184 joules over grams degrees C, times my final temperature, and I'm going to put this in brackets just to keep myself honest, 74.6 minus 8.50. And the units here are degrees Celsius. So I go ahead and I just go straight through it. 466 times 4.184 times 74.6 minus 8.50. It gives Evy a lot of kilojoules. Evy said a lot of kilojoules because Evy already knows the answer. The number you are going to get right now is going to be in joules. It's going to be very intimidating. It's going to scare you because you guys are not usually used to seeing these large numbers of joules. It's a very large number. This is common. This magnitude of numbers is going to be very, very common. And before I celebrate being done, I read the question. It wants my answer in kilojoules, so I have to convert. So I have 128.878 joules. 1,000 joules is 1 kilojoule. Notice my complete disregard for significant figures. I will fix them at the end. So this gives me 128.9 kilojoules. But, you know, I have to use significant figures and I need to have 3. My final answer comes out to 129 kilojoules. Ta-da! Math. So, the next thing, it is constant volume calorimetry. So this instrument is called a bomb calorimeter. It sounds like it's something really cool. Like you can explode bombs in here, but you can't. It's not as fun as it sounds. It is going to be a system in which no heat enters or leaves the calorimeter. You are going to have your thermometer and your stir. You will then ignite your material, and then based on the heat change of your water, which is going to be your surrounding, you can figure out the heat from your reaction. At UCCS, and here's hoping I'm not lying since this is Mr. Dion's students and mine, they used to have a lab in which they will burn a Cheeto to try to figure out how much energy you will get out of eating one Cheeto. And turns out that the calories in the food packages are surprisingly accurate. So if you ever want to feel like a really bad person, go ahead, burn your Cheeto and figure out how much energy you can get out of that. In this case, when we're looking at the Q of the system, so in this case, it will be the Q of the Cheeto. It will be the Q of the water. So how much water, how much heat is my water absorbing? Q of the bomb. So the bomb is going to be my calorimeter. Despite our best efforts, our systems are not perfectly insulated. They are always going to absorb or steal some of the heat from our reaction. And then you have Q of reaction. Q of system is going to come out to be 0. So my Q of reaction is going to equal minus their inverse of Q of water plus Q of bomb. You know how to find the Q of water, MC delta T. And for your calorimeter, your Q is going to equal your calorimeter constant times your change in temperature. So, this seems very daunting. It does. But I am going to walk you through how to do this calculation. So it says you have 1.435 grams of naphthalene, basically mothballs. You burn it in a constant volume bomb calorimeter. The temperature of the water went from 20.28 to 25.95 degrees Celsius. If the heat capacity of the bomb plus water was 10.7 kilojoules over degrees Celsius, calculate the heat of combustion of naphthalene on a molar basis. Okay, so here you have a lot of things to do. What I strongly suggest is that you highlight what you have. So I have temperature, initial, and final. I have a calorimeter constant. I also have grams and formula. I also write myself a note that delta H of combustion has units of kilojoules per mole. The reason why I write myself that note is that if I get lost in the problem, I know what my units should be, so I have a way of rescuing myself from the depths of bad math. Okay, so the first thing I need to do is find my calorimeter heat. So how much heat did my calorimeter absorb? How much heat is stolen by calorimeter? In order to do that, I use my calorimeter constant. So Q of cal is going to equal C of cal times your change in temperature. So that is going to be 10.7 kilojoules over degree C multiplied by 25.95 degrees C minus 20.28 degrees C. So I go ahead and I math it out. I have 10.7 times 25.95 minus 20.28. According to my calculator, that is going to equal 60.67 kilojoules. Okay. Now I have that Q of system is going to equal my Q of cal plus my Q of reaction. And I know that Q of system is 0. What that tells me is that whatever my calorimeter gained came from my reaction. So that allows me to say that Q of cal equals minus Q of reaction. Now I have Q. So my Q of naphthalene, oh no, there's a TH missing. It's going to be 60.67 kilojoules. Before I can claim victory, I look at my units. I need to have them in kilojoules per mole. Right now, all I have is kilojoules. So what I need to do now is convert my grams of naphthalene, my 1.435 grams, 1 mole of naphthalene is going to be 128 grams. That number came from the periodic table. It gives me 0.0112 mole. Yeah. So now, let me check my math again. 25.95 minus 20.28. So based on the numbers I have, I get this number. So my delta H of reaction is going to equal my Q of naphthalene divided by my mole. So I have my moles, I have my Q, I have a calculator. So that gives me delta H naught of reaction is going to be negative 60.67. Why negative? Whatever my calorimeter lost or gain came from my naphthalene. I do this, it gives me a lot of kilojoules, like a lot. So I get negative 5.42 times 10 to the 3 kilojoules over mole. Okay, that is my problem. This feels a little bit heavy. The good news is that for most of the chemistry we do, we don't use bomb calorimeters. What we tend to use is going to be coffee cup calorimeters. These are the fuel values of food. So usually, as I said before, what we use to measure calories in food is going to be a bomb calorimeter. Here are some of the energies of combustion you can release or absorb. So in order to break down cheese, you need to put in 18 kilojoules for every gram of cheese we eat. So if you're having a really bad day and you're eating like the whole half a pound of cheese, you can calculate how many kilojoules you need to actually burn off all the sad day cheese. However, beer releases 1.5 kilojoules for every gram of beer. Bread releases 11 kilojoules per gram. So technically, if you live on bread and beer, it's significantly healthier than just living on cheese. Like so much healthier, so much more stable, better for your health. Like so much better. Please do not consume just bread and beer. Please do not do that. I feel like I have to say it because otherwise you will do it. This is the kind of calorimetry we will do. For constant pressure calorimetry, we use it to measure delta H. And what you have to remember is that delta H is going to equal my Q at constant pressure. So what you have here in this very, very exotic setup is 2 styrofoam cups nested into one another. Sometimes if you have a fancy school, they have a styrofoam cover with a hole for the thermometer and a hole for the steering. If you go to a school that does not have as much money, we give you a square piece of cardboard and some tape and say best of luck. That is what we did at Clemson. So we're using the coffee cup calorimeter. What you're doing is you're measuring heat gained or lost by my solution, and water is going to be my surroundings. So for an endothermic reaction, my solution is going to get colder. For an exothermic reaction, my solution is going to get hotter. So when we're doing coffee cup calorimeter calculations, what we're looking at is the heat that is gained or lost by the solution. So my Q of solution is going to equal my mass of solution, total mass of solution, times the specific heat of solution, times the change in temperature of the solution. so that the minus Q of my reaction will equal the Q of solution. Basically, once again, whatever my solution is gaining is because my reaction released. It is going to be a case in which we can neither create nor destroy heat. We can only transform it between different systems. My delta H of reaction is going to equal the Q of my reaction divided by my moles. So once again, the units are going to help you out. Units here are going to be kilojoules over mole. Okay, so this is one of the problems that it is really, really, really fun to do. So it says that you have a lead pellet that has a mass of 26.47 grams. So this is going to be my mass at 89.98 degrees Celsius. So that's my TI. Was placed in a constant pressure calorimeter of negligible heat capacity, which means that technically it's a good calorimeter. On the other hand, it says it has 100 mils of water. I wonder why they're telling me this. This is going to be your mass of water. It tells you that the temperature of the water rose from 22.5 to 23.17. So this is TI of water, the 22.5. The final temperature is going to be 23.17. So we set this up in a way that Q of lead is going to equal minus Q of water. Why? Because whatever your water gained had to come from the lead. There is no other way this could have happened. We are not making stuff up. It doesn't matter. Okay? Doesn't matter. We have to do this. So I go ahead and I start with my lead. So I have 26.47 grams times a number I don't know. Final temperature of lead is going to be the same as the final temperature of water minus the initial temperature of the lead. That is going to equal minus the mass of water, which is 100 grams. Where did you get 100 grams for? Well, we have 100 milliliters of water. We are going to make the assumption that the density of water is 1 gram over milliliter. So we go ahead and convert those 100 grams into those 100 milliliters into grams. The specific heat of liquid water is 4.184 joules over grams degrees C. We got that value from a table. Final temperature is 23.17. Initial is 22.5. I solve everything on the left-hand side. So 100 times 4.184 times 23.17 minus 22.5. It gives Evy negative 280.328 joules. On the other side, I have 26. I'm going to solve my delta T just to make my life slightly easier. 23.17 minus 89.98. It gives Evy negative 66.81 degrees C. So now I have 26.47 times negative 66.81. It gives me negative 1768.4607 grams degrees C. Specific heat. You're like, this units kind of sort of make sense. Yes, they do. That is the point of units. So my specific heat, I have negative 280.328 joules divided by negative 1768.4607 grams degrees C. Notice that I am keeping the calculator vomit. I will use my significant figures at the end. I math it out, and I get 0.1585152557 joules grams degrees C. Once again, calculator vomit. This goes ahead and gets fixed to 0.1585 joules over grams degrees C. Ta-da! Calorimetry. These are going to be some of the heats of reactions that you may encounter. In lab, the reaction you're going to be trying to find out the delta H for is going to be heat of neutralization, in which you have an acid and a base forming sodium chloride in water in the liquid form. The value for that is going to be negative 56.2. That is going to be the value you guys are shooting for in the lab. Usually, the larger the magnitude of your negative number, that means that your products are going to be significantly more stable than your reactants. So in this case, the reaction of magnesium chloride with sodium in the liquid state to make sodium chloride and magnesium solid, my products are more stable than my reactants. Okay, that is all I'm trying to say here. So let's go and walk through how to do this problem. We are gonna try to do this. It says, what is delta H of reaction in kilojoules per mole of HCl consumed for the following neutralization reaction when you have 50 mils of 1 molar hydrochloric acid and 50 mils of 1 molar sodium hydroxide. The temperature changes from 25 degrees Celsius to 31.5 degrees Celsius. Assume that the specific heat capacity of the solution is going to be the same as water, and that the density of solution is the same as water. If this problem seems familiar to you, it's because it is. This is what you're doing in lab. This is what you will be doing in lab. So, first question. What are we calculating? What is our final volume? So we have 100 milliliters of solution. We have an initial temperature. We have a final temperature. So, which equation should I use? I have mass. I have total mass. I have specific heat. And I have initial and final temperature. Not in the order I circled them, but we have initial and final temperature. Because we have that, the equation we should be using is Q equals MCAT. From there, we have to find what our delta T is going to be. So our delta T is going to be our final temperature, 31.5 degrees Celsius, minus the initial temperature, 25 degrees Celsius. So go ahead, do that calculation really quickly. Tell me what your delta T is. Yeah, letter D, 6.5 degrees Celsius. Guys, I know this seems silly, but sometimes you have to break down the question. It makes things easier. It really, really does. After we have our delta T, we have to ask ourselves, what are we actually calculating? Are we calculating the Q of surroundings, or are we calculating the Q of reaction? Technically, we can only calculate the Q of surroundings. Okay, that is the one thing we can always calculate, and that is going to be Q of surroundings. So that is what we're doing. Okay. From there, we ask ourselves, which mass do we use in our calculation? 50 grams, 100 grams, the mass of 1 mole of hydrochloric acid, or the mass of 1 mole of hydrochloric acid and 1 mole of sodium hydroxide. What we are actually measuring is solution, correct? The solution is my surroundings. So the mass of my solution, my 50 milliliters of acid plus my 50 milliliters of base, that is the mass I need to use. So I'm going to quickly solve for Q of surroundings, and that is going to be 100 grams. Why 100 grams? 50 milliliters of base, 50 milliliters of acid, times the specific heat of water, times my change in temperature, which was 6.5 degrees Celsius. I multiply, so I get 100 times 4.18 times 6.5, and that gives me a Q of surroundings that is 2717 joules. That is the heat that my surroundings are absorbing. But that is not the Q of my reaction. So the Q of surroundings is 2717 joules. Q of reaction plus Q of surroundings must always equal 0. Whatever one is gaining is being lost by the other one. So my Q of reaction is just going to equal my minus Q of surroundings. So my Q of reaction is going to be what? It's going to be a negative number, correct? So when I have a negative number, once again, I eliminate the two that are positive. That was me almost dropping my computer. You're fine. And from there, I realized that my answers are in kilojoules, and the number I found was in joules. So I need to go ahead and convert to kilojoules. So I do it. So I have negative 2717 joules. There's 1,000 joules in 1 kilojoule. My answer is going to be negative 2.7. That is the Q of my reaction. The last part of this problem is going to be calculating the delta H of reaction. So now I look at my units. I want it in mole of HCl. So my Q of reaction, we already determined it was negative 2.7 kilojoules. What I now need to do is figure out how many moles of hydrochloric acid I have. So how do I do that? I have to start by using my milliliters. So I have 50 milliliters of hydrochloric acid. According to the metric system, in 1 liter of hydrochloric acid, you have 1,000. That's a 1. It was always a 1. It was never a 5. 1,000 milliliters of hydrochloric acid. We now use our molarity as a conversion factor. Why? Because big M is just going to be moles over liters. So what I do is I assume I have 1 liter. Then I have 1.0 mole of HCl. That gives Evy 0.05 mole of HCl. In order to find delta H of reaction, I'm going to have negative 2.7 kilojoules divided by my 0.05 mole. So go ahead and do that calculation. Keep in mind 2 things. My sign has to be negative, so I eliminate this and I eliminate that one. My delta H has to be a negative number. So what is my value for my delta H of reaction? Negative 54 kilojoules per mole. Ta-da! The last thing we have in this section is going to be another problem including calorimetry. So let's look this over. It says I have 100 milliliters of 0.5 molar hydrochloric acid that I mixed with 100 mils of 0.5 molar sodium hydroxide in a constant pressure calorimeter. My initial temperature was 22.5. My final temperature was 25.86. The question is, calculate the heat change of the neutralization reaction on a molar basis. Assume that the densities and specific heats are going to be the same as water. So the strategy for this is 1, figure out which equation to use. So I'm going to use Q equals MC delta T, and then I'm going to use delta H of reaction. It's going to be Q of reaction divided by mole. Then 2, I have to figure out mass. Figure out mass of solution. So in this case, I have 100 mils of acid and 100 mils of base. I have 200 milliliters of solution. Because it's telling me that I have the same density as water, I can make the assumption that I have 200 grams of water. So for step 3, I calculate Q of solution. So that is going to equal my mass, my 200 grams, times the specific heat, times the final temperature, 25.86, minus 22.5. So that is going to give me the Q of my solution. 200 times 4.18 times 25.86 minus 22.50. It gives Evy a Q of solution that is going to be 2808 joules. Okay. Step 4 is going to be Q of solution plus Q of reaction equals 0. So then that means that Q of reaction equals minus Q of solution. In this case, Q of reaction is just going to equal negative 2808 joules. Okay. Step 5. Find moles of water produced. So we are going to use water in this case because you guys have to use water in your lab, and it's just going to be a way of doing this. So I have 100 milliliters of HCl. 1 liter is going to equal 1,000 milliliters. According to my molarity, in 1 liter, I have 0.5 mole of HCl. According to the balanced chemical equation, for every 1 mole of HCl, I produce 1 mole of water. So I end up getting 0.05 mole of water. Step 6, calculate delta H of reaction. And that is going to be given by using Q of reaction divided by your mole. So I have negative 2808 joules divided by 0.05 moles. This is going to give me a very large amount of joules, okay? 2808 divided by 0.05, I get 56160 joules per mole. But the units I want to use is going to be kilojoules per mole. So I divide by 1,000, and my final answer comes out to negative 56.2 kilojoules per mole. Okay, this is the end of this section. In the next section, we are going to look at indirect measurements of enthalpy of solution or reaction, and we're also going to look at how to calculate enthalpy of reaction in different situations.